Today's video is going to be on empirical formula, and in this video we're going to cover a couple of topics including ratios, Dalton, and atoms. The first thing that we're going to do is we're going to define empirical formulas. Empirical formulas are a formula giving the proportion of elements present in a compound, but not the actual number of the arrangement of atoms. So we're just looking for the ratio or the proportions of one element of a compound compared to another one. An example that we can use is glucose. We know that the formula for glucose is C6H12O6. But the empirical formula is going to be CH2O. And the reason for that is that we have just reduced this down to its lowest terms. One of the reasons that we can do this has to do with one of the founders or old guys of chemistry named Dalton. And Dalton had a set of 6 postulates that he made way back in the day. And some of these have been disproved. So for instance, we know now that atoms can have different masses, slightly different atomic masses. But in general, the thing that is most important for us is his postulate here that atoms of different elements combine in simple whole number ratios to form chemical compounds. And that postulate that he made is something that we're still using today. We know that atoms come together in whole number ratios when they make a compound, and that's how we can figure out our empirical formula. There are a couple of steps that we need to follow in order to figure out our empirical formula, but there's one general overarching theme that we need to keep in mind. And that's that an empirical formula can be found by comparing the number of moles of one element to the number of moles of another. And that's our main goal in finding an empirical formula. So even though we're going to have different methods for finding the mole, in general, if we can find some sort of shortcut to find what the moles are, that's our main goal, is comparing those moles of compounds together. So as an example, we can go ahead and say that we have a compound that is made of sodium and oxygen, and it has 18 moles of sodium, and then it has 9 moles of oxygen. So we've done our experiment, and we find this many moles of each of our chemicals. We can go ahead and compare those and get them to the lowest common denominator. We can see that since we have twice as many moles of sodium than we do oxygen, that we should have a ratio of 2 to 1. And in this case, we would have a ratio of 2 to 1, and this would be sodium oxide. Example number 2 is going to be iron and chlorine. We find that we have 230 moles of iron and 695 moles of chlorine. Now, this particular case, if we did the math, we would find that we have slightly more moles of chlorine than a whole number ratio. Often when we do our experiments, it's going to be that way. We're going to have a slight difference because of either some rounding error or some error in the actual equipment that we use to measure this. So as long as we get to a place that we can go ahead and estimate what the ratio is, we're going to be in a good spot. So in this case, 230 is about 1/3 as much as the 695. Therefore, we could say that we have 1 iron to every 3 chlorine. And the compound would be iron 3 chloride, which has the chemical formula of this right here. Now, most problems that use mass and mass percent are going to come in a form that requires a little bit of calculation, and we can go ahead and do some roundabout ways of calculating it out. A majority of problems that you're going to see are going to go ahead and give you some number of each compound that you have, and then we'll have to go ahead and figure out the percent. A majority of problems are going to come in this form and can be easily solved by this one. But what I want you to take note of, especially as you're writing down these steps, is that the main goal, the main point of the empirical formula really starts at step 3. Steps 1 and 2 are just us trying to figure out how many moles of a compound that we can that we have to compare. Step 3 is us actually comparing the moles to get the chemical formula. So let's go ahead and do a problem that starts and uses empirical formulas. This problem here is a basic problem, and what it does is it says that we have a compound that contains 32.65% sulfur, 65.3% oxygen, and 2.04% hydrogen. And it's asking us, what is the empirical formula of this compound? So what we're going to do is our first step is normally to get it to a percent. This question was gracious enough that it already gave us a percent, so we can go ahead and take that percent directly. We know that we have this percent, and now what we're going to do is we're going to go ahead and assume that we have 100 grams of this compound. And the reason that we're going to assume that we have 100 grams is because that's the laziest way to turn a percent into grams in this case. So if we have 100 grams and 32.65% of it is sulfur, then guess what? We have 32.65 grams of sulfur. The same goes for our oxygen. Our percent of 65.3% directly relates to the grams, and the same also goes for the hydrogen. So we also have 2.04 grams of hydrogen. And once we have grams, we can go ahead and use our molar mass to figure out our number of moles. So we would go ahead and take the 32.65 grams of sulfur, and we're going to divide that by the molar mass of sulfur. And that'll give us 1.019 moles of sulfur. The same goes for oxygen. We end up getting 4.08 moles of oxygen, and we do the same for hydrogen as well. So we now have our moles. Now we can compare our moles, which is our main goal. We're going to compare our moles by dividing by the lowest number of moles. And in this case, we have the lowest number of moles being 1.019. So we take the moles of sulfur, 1.019, and divide that by 1.019, which means that this compound ends up having 1 sulfur. It has the ratio 1 sulfur. Then we go ahead and take the number of moles of oxygen, which is 4.08, and we also divide that by 1.019. And it tells us that we have a ratio to about 4.003 of oxygen. The last one we do is hydrogen, and hydrogen ends up being 1.98 for the ratio. From here, we can go ahead and just condense it down. We know that the 4.003, well, that's just about 4. So we know that this ratio is going to be 1 sulfur to 4 oxygen to 2 hydrogen. And from there, you can go ahead and arrange it in any form that you want. In this case, I can take a pretty good guess that this is going to be sulfuric acid just based off of the chemicals that are there and the proportions. So we end up making the formula of H2SO4. This next question is going to be a little bit harder, and it has a couple of different thought processes going through it. So I'm going to go ahead and pause so that you guys can go ahead and write down this question. Okay, that should have given you time to pause. From here, what we are going to do, we're going to go through how to solve this question, and we're going to keep one thing in mind, especially when we're solving it here. We're going to keep that fact that we are going to be looking for the empirical formula. So our end goal is to go ahead and find some way that we can get to moles of a compound. And it doesn't really matter how we get to moles of each compound or even to grams of each compound, which the first questions are asking here. As long as at the end we end up getting the right amount of grams for this compound or moles for this compound to go ahead and solve for the empirical formula. So, for question number 1, it is specifically asking us to go ahead and solve for the mass in grams of C in the 1.2359 gram sample of the compound. Okay. So, we have this compound. It has carbon, hydrogen, nitrogen, and oxygen. It says that we take our sample and we burn it in excess oxygen, and we end up forming 2.241 grams of carbon dioxide. Okay, so right away, I see that we have a reaction and we get carbon out of it. Okay, I can go ahead and say, okay, this is great. We have 2.241 grams of carbon dioxide. Now, we have to go ahead and figure out how many moles of carbon dioxide that is, because that's going to be important for our question later. In order to figure that out, we have to divide that by 44.01 grams. Okay. The reason we divide that by 44.01 grams is that's the molar mass of carbon dioxide. That's how much 1 mole of carbon dioxide weighs. And that will end up giving us 0.0509 moles of carbon dioxide. The last part is that we just need to get it into grams. We already know that if we're going to get something from moles to grams, we have to multiply by the molar mass. And since there's only 1 mole of carbon in each mole of carbon dioxide, we just have to multiply by the molar mass of carbon. So in this case, we end up getting 0.6113 grams of carbon in this compound. This next question is asking for N, okay? And this is going to be a case where we want to try and find the laziest way to figure out all of these answers, especially if it's in a free response type question like this. And it's saying that when we found N, that it ended up making 28.84%. And theoretically, we could go ahead and try and do some sort of percentage move here, or we could go ahead and multiply that 28.84% times the amount of mass that was in our initial sample, because this 28.84% came from here. So all that we have to do is multiply the 1.2359 grams times the 28.84 in a decimal form instead of percent, and that's going to give us our grams of nitrogen. And we have grams of nitrogen. We'll have to turn that into moles eventually, but not quite yet. Okay. Next, it wants us to determine the mass in grams of the oxygen in the sample. Okay. So we have our total mass, which is the 1.2359, and we're going to subtract from that the mass from the nitrogen. We'll subtract the mass from the carbon, and then we'll subtract the mass from the hydrogen, which is given to us in the problem. And that'll give us our total mass in grams of oxygen. The last part is our final question, figuring out the empirical formula for this compound. This empirical formula, we already determined and have all of our grams, so we can go ahead and start by writing that down. So we have our nitrogen, carbon, hydrogen, and oxygen. From here, we need to go ahead and get them into the mole. So we'll go ahead and divide by their molar mass. And that will give us the number of moles of each compound. Since we have the number of moles of each compound, we can go ahead and divide by the lowest number of moles. And I can see right here that the lowest number of moles that we have is the 0.0127 moles of oxygen. So we'll divide everything by that, and we will end up getting a ratio that looks like this. Our final step is just put it into the formula. Here, our formula would end up being C4H6N2O. This concludes the lecture for empirical formula. You can now go ahead and move on to the next video.